Alright, so this is page 263, number 6. So number 6 says, sketch the curve y equals 9 minus x squared, stating the coordinates of the turning point, also known as the vertex or the stationary point, and of the intersections with the axes. So if I go ahead and sketch this out, what I'm going to notice is I'm up here at 9. Well, basically, if I rewrote this in general form, what I'm going to notice is my parabola is actually turned upside down, it's reflected, and my y-intercept is 9. Since I have no b term, that also means that my vertex happens at 0, 9. So here's my vertex, I'm doing it in a different color, at 0, 9. And basically I know my parabola is going to go down like, it's going to be symmetrical if I can draw it correctly. Okay, it's going to look something like this, okay, like that. Alright, so basically I know this point is 0, 9, and now I need to find the point at which, or the points at which the graph intersects the x-axis. Well, the easiest way to do that, which you all should know, is that x-intercepts happen when y is 0. So if I substitute 0 for y and solve for x, I end up with x equaling plus or minus 3. So I'm going through this really fast because I'm sure that you all know how to do this because this is a review from last year. So my roots are negative 3, 0 and positive 3, 0. Alright, so, oops, I don't want to delete all of that. Just grab part of it. Of course not, that would be too easy. Okay, so basically, the next part says find the area of R. Oh, and then it says the finite region bounded by the curve and the x-axis is R. So let me highlight R for us. So there's part of R. By the way, this half is equal to the volume and area of this half, okay, because they're symmetrical. The problem is calling this whole purple area region R, that whole thing. So part A says that we are to find the area of R, and hence, or otherwise find, and then they give us an integral. They give us this. Okay, you might be thinking, oh, that's great, they set up an integral and we're actually going using 0 to 9, which is, we're doing the area in terms of y, which is absolutely fine, okay? But what you should notice, hopefully, is that I've only got half of my curve, right? Because the square root of 9 minus y, well, the biggest value I could put in for y is 9, right? And if I put something smaller in, I'm only going to be getting a positive out, which tells me that I'm only finding the area of this part, okay? Because it doesn't matter what I put in for y here, I'm not going to end up getting a negative out of this square root. So what we need to do is we need to rewrite this and say that we're going to be multiplying our result by 2, because this half has the same area as this half, so we could just double it. So I'm going to go ahead and raise this to the half power, because I think that's easier to do, and then I'm going to integrate. So 2 times, okay, so if you'll remember, when we're doing a binomial, right, that has a power, the variable has a power of 1, all I'm going to do is I'm going to say 1 divided by the coefficient of my variable, which in this case is negative 1, times 1 divided by my new exponent. So when we integrate, we add 1 here, but when I'm adding 1 to half, that's like adding 2 over 2. So that means I'm dividing by 3 halves, right? Because that's my new exponent times what's on the inside, raised to the new exponent. Alright, and then we're going from 0 to 9. Alright, so I'm just going to simplify this up. So I end up, and I'm just going to do the math here pretty quickly because I think you should know this. We've been doing a lot with fractions. This, when you multiply it together, equals negative 2/3, right? Because we're going to multiply this by its reciprocal to get it out of the denominator. So that's why we get a negative times a 2/3. To get negative 2/3, 9 minus y to the 3 halves. Okay, from 0 to 9. Okay, so let's go ahead and plug in. So we're just going to leave the 2 hanging out front there. So we end up with negative 2/3 times 9 minus 9 is 0. I already knew that coming in because I can observe that. And then I'm going to take away from that negative 2/3. For y, I'm going to put in 0 this time. 9 minus 0 is 9 to the 3 halves. All right. So, let me put a parenthesis. Okay, so I end up with 2 times 0 plus, right, negative times negative. So I end up with 9 to the 2/3, which is 27, times 2/3, um, which is 18. No, I lost my mind for a second. All right, so we end up with 2 times 18, which means my total area is 36. Okay, so the area underneath the curve has a value of 36. Okay, and if we think about that in terms of area of a rectangle, if I were to draw a rectangle here, right, my base has a width of 6, my height is 9, so the area of that whole rectangle would be 54. The area underneath the curve we said is 36. That sounds pretty reasonable because we have all of this space here and here, right, that's not included. So that seems reasonable. Okay, so that's kind of how we can look at our answer and see, does it really make sense? So, I think it does. All right, so let's then move on to part B. Just going to clear a little of this off here. Okay, all right, so part B says that we are going to find the volume of the solid of revolution obtained when r is rotated 360 degrees about the x-axis. Okay, so we're taking this whole region and we're rotating it about the x-axis. Alright, so if I do this, I'm going from, my boundaries are negative 3 to positive 3, and if you wanted to do 0 to 3 and multiply it by 2, which I think I'm going to do, well, I'm not going to do it this time, but I like doing that because I like having 0 as an option because it's faster. You could totally do that because this is going to have the same volume as this, so you can just double it. But I'll do it this way to show you what I mean. Okay, so since we're rotating about the x-axis, we need y to be squared. So I'm going to take my original equation and I'm going to square it. Okay, so I'm going to pull pi out front also because it's pi r squared, right? This is the r part. Okay, so we end up with 9 minus x squared raised to the power of 2 dx. Okay. Now, you might be thinking, oh, I can use the chain, or I can undo the chain rule, but here's the catch. We haven't learned how to deal with an exponent within the parentheses yet. So really what we're going to do is we're going to FOIL it out and simplify it that way. So we end up with, well, I'm going to write it over here for us. 9 minus x squared times 9 minus x squared, right? So we end up with 81 minus 18x squared plus x to the 4th dx. Okay? And if you figured out how the chain rule works without having to FOIL, that's great, but we haven't gotten there, so I would recommend doing this for now. Alright, so let's integrate. So we end up with pi times the integral of 81 is 81x minus 18 divided by 3 x cubed, or 6, plus 1/5 x to the 5th, and we're integrating from negative 3 to positive 3. Oh, there's my work from the last problem. I'll get that out of here. Okay, so basically everywhere I see x, I'm going to start by putting in positive 3. Okay, and I'm just going to leave pi hanging out here. I'm not going to attach it yet. So I'm going to go ahead and put positive 3 in everywhere. So positive 3 here, minus 18 divided by 3 is 6, times positive 3 cubed, plus 1/5 times positive 3 to the 5th. Okay, and this is where I need to subtract. And I'm not just subtracting part of it, I'm subtracting every single term. So I end up with 81 times negative 3 minus 6 times negative 3 cubed plus 1/5 times negative 3 to the 5th equal. Alright, so I just plugged this into my calculator and I ended up with pi times 259.2. And I was using my graphing calculator, which is why I'm not getting the same fraction that you would if you're using your Casio. So the book gives a fraction, but that fraction is equivalent to this value. Okay, so that is part B. So now we're going to move to part C. So I'm going to get rid of this so we can see the picture again. Alright, so let's do part C. So part C says, find the volume of the solid of revolution obtained when R is rotated 360 degrees about the y-axis. So I'm going to be rotating now this way. Okay, which means that we need to solve our equation in terms of y, but if we think back to the very first equation that we did, it was already rotated about, or is already solved for x, so that makes life a little easier. So basically, I'm going to say pi times, I'm integrating from 0 to 9 because I'm using the y-axis, and then what I'm going to do is I'm going to put in x squared dy, right? So if I look at my original equation, I end up with y equals 9 minus x squared. And I'm going to get x squared on its own side, okay, which gives me 9 minus y. So that's what I'm going to put in straight away for x squared. Okay, so I'm timesing pi by the integral from 0 to 9 of 9 minus y dy. Alright, so let's integrate. There I have my old work. Alright, so, okay, so the integral of 9 is 9y, and remember we're in terms of y, which is why our integral is going to have y in it, minus the integral of y is half y squared, okay, and that is happening from 0 to 9. Alright, so let's go ahead and solve this. So we end up with 9 times 9 minus half times 9 squared, okay? You know, and technically we should be correct about this, and now we're going to put in 0, right? 9 times 0 minus half times 0 squared. Well, we technically end up subtracting 0, so you don't really have to do that for this particular problem. So, I just wanted to show you how you do that normally. So let's go ahead and do this. We end up with pi times 81 minus 81 minus 81 halves. Okay, so 81 minus 81.5, 81 minus 81 halves is pi times 40.5. So that means our volume is 40.5 pi. Alright, there you go.